Okay, well, thank you very much for your introduction. My name is Alejandro Bacigalupe, and I'm going to present our recent results in protein-based materials, particularly in adhesives based for wood industry. So, for starters, uh, I work at INTI. This is an organization, a public organization that make developments for technological transfer to the industry. For those of you who likes geography, we are here in Buenos Aires. And like you say, Gurgus, our department work in composites materials, particularly in bio-based adhesives, natural fiber composites, and valorization of agricultural residues. So why black soldier fly? I believe you know more of this topic than me, but black soldier fly is expanding worldwide, mainly because of the efficient waste conversion and the possibility of obtain meals with high protein content. In our work, we work with meals or fries that were fed with potatoes waste, particularly French fries, and we use meals with high protein contents. Then we make adhesives, and with these adhesives we make particle boards. So we can convert residues in high added value materials. But like most of you know, black solder fry mills are not industrial uniform. Here we have some images of three mills that we use in our work that visually they are already very different. We make some analysis to know the composition of these mills. We can see that protein content was also very different between them, and also other contents in these mills, like lipids. Of course, for our use, that is adhesives, we defatted all the mills with hexane because fat is anti-adherent, so it's a problem for us. So our question was if does batch-to-batch variability in BSFL mills implies variability in the adhesive performance. In other words, if two mills could have very different mechanical properties when making the works, because if we're thinking in massive production of particle boards, this could be a problem. For doing this, we try to standardize the formulation and the processing conditions. You can see here the formulation. It was a very simple formulation with meal, water, and sodium hydroxide to denature the proteins. Of course, protein adhesive formulation can be very complex, but for starters, we start with this formulation. So the key is that differences in the results are exclusively from the raw material variability. We make the boards, we test in the mechanical properties of these boards, and here you can see some images of the boards we made. Board A has very good mechanical properties. The board B and C does not. Also, board B, you can break it by hand, so it was really bad. What we do, I don't know if you are familiar with mechanical properties, but we test it in tensile strength and bending strength also. So we have one sample with very good mechanical properties, one with poor mechanical properties, and one with non-mechanical properties. So first, we think the results for meal B is expected because the low protein content, because the theory of adhesion for protein-based materials based on functional groups that are in the protein that could interact with the functional groups in the wood surface. Of course, this was not all because sample C has similar protein content that sample A, but mechanical properties were quite different. So protein content does not explain all the difference between the adhesives. So our next text was rheology. Protein adhesives act as non-Newtonian materials, and viscosity has a very important role in wetting of the wrap surface. If you have an adhesive with low viscosity, you will have an uniform and good wetting of the wood. If you have a sample with high viscosity, like was B and C, you will have poor wetting properties. So we believe that for sample C, one factor that is affecting the mechanical properties is the rheology of the adhesives. Then we try to get to know a little bit more of our mills. So what we do was thermogravimetric analysis, TGA. We have studied the thermal decomposition of the three samples. And here we saw some very interesting results. For example, in the zone of the organic fraction stability between 200 and 400 degrees, we saw that sample A has very different stability than sample B and C. We can see in here a little bit of a shoulder at 200 degrees, and at near 400 we also have see um, some differences in the thermal decomposition. But for us, the most interesting result in this test was this decomposition peak at 700 degrees. At this point, all the organic matter was already decomposed. So we were start to searching why one sample has not this peak, but B and C has it. So looking into the literature, we saw that this could be by the cause of calcium carbonate, calcite, that it can be abundant at later larval stage. I'm not a biologist, so sorry if I'm saying something wrong. But if sample C, B and C have calcium carbonate and A no, calcium carbonate can act as a filler in many adhesives, so that could be the reason for the high viscosity in the adhesives with these samples. So this is give us a theory if larval stage can also play a role in the performance of the adhesives for particle board production. So, well, this is a very short presentation and it's ongoing work, but for now, our key finding is that batch-to-batch variability strongly impacts in adhesive performance. We kind of already knew that. But for us, the most important was that protein content alone does not explain the behavior of these adhesives. Rheology always affects the wetting property. And most important, we have this question if larval stages can act as a key role in order to use these mills for protein for particle production. So I think this could be a very good opportunity to connect insect nutrition with material design. We Our experience is in material designs, not much in insect nutrition. So I think that this type of works could be the most interesting to do. So thank you very much. I'll leave here my email and also a QR code. This has some more info about our research topics and some of the papers we publish in this matter. So thank you very much once again, and look forward for your questions.